Imagine a universe fresh from its birth, a roiling incandescent chaos of gas, dust and untamed energy where the very idea of structure seemed impossible. Yet from this wild disorder galaxies arose, sprawling luminous tapestries of stars, planets and cosmic wonders that give the cosmos its grandeur. How did the universe transform from a formless void into the intricate galaxies that dazzle us today? In this exploration, we'll unravel the epic story of galaxy formation, journeying from the Big Bang's fiery dawn to the elegant spirals, ellipticals and clusters that define the night sky. It's a tale woven by gravity's patient hand, punctuated by cataclysmic collisions and the alchemy of stardust. Join us to discover how galaxies were forged, what forces shaped their paths, and why they hold the key to understanding our cosmic origins. To understand how galaxies came to be, we must rewind 13.8 billion years to the Big Bang, the singular moment when the universe exploded into existence. In its earliest microseconds, all of reality was compressed into a point of infinite heat and density, a seething maelstrom of quarks, gluons, electrons and photons locked in a chaotic plasma. No stars, no planets, no structure, just pure frenetic energy. Within seconds, as the universe expanded and cooled, quarks coalesced into protons and neutrons, the building blocks of atomic nuclei. By 3 minutes, these nuclei fused into the first elements, about 75% hydrogen, 24% helium, and a sprinkle of lithium. But the cosmos remained a featureless haze too hot for atoms to form. It wasn't until 380,000 years later, during an event called recombination, that the universe cooled enough for electrons to pair with nuclei, creating neutral atoms. This shift unleashed a flood of light, now detectable as the cosmic microwave background, a faint echo of the universe's infancy. You know, this early cosmos wasn't perfectly smooth. Subtle density fluctuations, variations of less than 1 part in 100,000, speckled the gas. Born from quantum ripples in the Big Bang's earliest moments, these tiny irregularities were the seeds of all future structure, galaxies, clusters, and beyond. Gravity was the master force that turned those delicate seeds into galaxies. In regions slightly denser than their surroundings, gravity's pull was stronger, drawing in more gas, dust, and particles. This process, known as gravitational collapse, amplified these differences over millions of years, transforming faint ripples into substantial clumps. In the densest cores, pressures and temperatures skyrocketed, igniting nuclear fusion and giving birth to the first stars, known as Population 3. These behemoths, often hundreds of times the sun's mass, burned fiercely and briefly, exploding as supernovas after mere millions of years. Their detonations scattered heavier elements, carbon, oxygen, silicon, magnesium, into the surrounding gas, enriching it for future stellar generations. As these stars formed and died, they clustered within their parent clouds, creating the first proto-galaxies, small chaotic assemblies of gas, dust, and light. Supernova shockwaves stirred the mix, while gravity pulled more matter inward, setting the stage for larger structures. From this turbulent chaos, the earliest outlines of galactic order began to take shape, as gravity wove a fragile web of connection across the cosmos. The first galaxies, emerging between 200 and 500 million years after the Big Bang, were raw and unruly. Unlike the graceful spirals or compact ellipticals we see today, these proto-galaxies were shapeless, turbulent clumps, more like cosmic storms than organized systems. They teemed with massive Population 3 stars, whose intense light and explosive deaths filled the early universe with bursts of energy and newly forged metals. Dark matter was a silent but crucial partner in this process. Making up roughly 27% of the universe's mass energy, dark matter exerts gravity without interacting with light, forming invisible halos around dense regions. These halos acted like gravitational molds, anchoring gas and stars as proto-galaxies grew. As the universe aged, small proto-galaxies didn't stay isolated. They collided and merged, forging larger, more organized systems. These mergers were cosmic spectacles, not gentle unions but violent mashups of stars, gas, and dust. When two galaxies met, their dark matter halos fused first, pulling their visible contents along. Gravity then reshaped the chaos, molding the material into new structures, flattened disks, sweeping spiral arms or dense elliptical spheres, depending on the collision's dynamics. Spiral galaxies, like our Milky Way, likely emerged when mergers preserved the gas's angular momentum, forming rotating disks where stars aligned in elegant patterns. Elliptical galaxies, by contrast, formed from messier crashes that scrambled gas and stars into rounded stable systems. These mergers weren't just about size, they triggered bursts of star formation as colliding gas clouds compressed, igniting new stellar nurseries that lit up the cosmos. The Milky Way's own story is one of conquest. Streams of stars like the Gaia Enceladus remnant mark smaller galaxies it devoured billions of years ago. Looking forward, in about 4.5 billion years, our galaxy will collide with Andromeda, merging into a vast elliptical galaxy, a new chapter born from chaos. Galaxies didn't just grow physically. Their chemical composition transformed over time, a process critical to their development. The first stars, made almost entirely of hydrogen and helium, were elemental forges, fusing lighter nuclei into heavier ones. Carbon, oxygen, nitrogen, iron, deep in their cores. When these stars exploded as supernovas, they hurled these metals, in astronomy, any element beyond helium, into the interstellar medium, forever changing the cosmos. This chemical enrichment fueled galactic evolution. Early galaxies buzzed with supernovas, rapidly boosting their metal content. Second-generation stars, known as Population 2, formed from this enriched gas, followed by metal-rich Population 1 stars like our Sun. These later stars could spawn rocky planets with complex chemistries. Earth's granite cliffs, iron core, or oxygen-rich air owe their existence to this cosmic alchemy. Without metals, planets as we know them wouldn't exist, nor would life as we understand it. Enrichment wasn't uniform. Galactic cores packed with stars became metal-rich quickly, forming bright disks of young, vibrant suns. Outer halos, home to older stars, remained metal-poor, preserving echoes of the early universe. This chemical diversity gave galaxies their unique identities, turning the chaotic byproducts of stellar explosions into the ordered ingredients of planets, moons, and potentially life-bearing worlds. At the heart of most large galaxies lies a supermassive black hole, with masses ranging from millions to billions of times the sun's. These cosmic giants are far more than silent voids, they actively shape galactic destinies. But how did they form? And how do they impose order on chaos? In the early universe, supermassive black holes likely emerged from the collapse of massive gas clouds or mergers of smaller stellar black holes. As galaxies grew, these black holes gorged on gas, dust, and stars swelling in size. Feeding black holes create glowing accretion disks, swirling maelstroms of matter that emit powerful jets of energy, heating nearby gas and sometimes stifling star formation. This feedback process acts like a cosmic thermostat. In active galaxies like quasars, black holes unleash torrents of radiation, sometimes expelling gas entirely and slowing galactic growth. In the Milky Way, our black hole, Sagittarius A*, is now calm, but its past outbursts likely helped regulate star formation, maintaining balance. Black holes are galactic conductors, orchestrating the chaos of growth into structured, sustainable systems, ensuring galaxies evolve rather than collapse under their own weight. Galaxies don't float alone. They're part of a vast network of clusters, superclusters, and filaments known as the cosmic web. This intricate structure also traces back to the universe's chaotic origins. The density fluctuations that sparked galaxies extended to larger scales, creating regions where matter gathered, and others where it thinned into voids. Galactic clusters like the Coma cluster bind hundreds or thousands of galaxies with gravity, surrounded by hot gas glowing in X-rays. Superclusters, such as the Laniakea supercluster encompassing the Milky Way, stretch across millions of light-years, linking galaxies in a cosmic dance. Filaments, thread-like bridges of gas and dark matter, connect these clusters while walls and voids complete the web's pattern. Dark matter is the web's architect, its gravity shaping the distribution of galaxies like an invisible hand. Without it, matter wouldn't have clumped so efficiently, leaving a far messier universe. The cosmic web is gravity's masterpiece, transforming a uniform cosmos into a structured lattice that showcases order on the grandest imaginable scale. Galaxies are not eternal snapshots, they evolve, their stories unfolding across cosmic time. In the Milky Way, star formation will continue for billions of years, crafting new suns from dwindling gas reserves. But as gas runs low, starbirth will slow, and our galaxy will gradually dim, its spiral arms fading into memory. In about 4.5 billion years, the Milky Way will face a dramatic transformation, colliding with the Andromeda Galaxy. This merger will blend their stars, gas and dust into a new elliptical galaxy, reshaping their ordered structures into something entirely different. Beyond our local group, the universe's expansion, driven by dark energy, will pull distant galaxies farther apart, potentially isolating our merged galaxy in a vast cosmic solitude billions of years hence. Yet even as the universe changes, the order forged in its youth, disks, clusters, webs, will leave lasting imprints in the stars and systems that endure. Future telescopes, paired with ever more powerful simulations, will peel back more layers of galactic history, from the earliest proto-galaxies to the dynamics of modern mergers. Galaxies are living narratives, their order a testament to a universe that continues to evolve, beckoning us to follow its story. The formation of galaxies is the universe's greatest epic. From the Big Bang's chaotic blaze to the spirals, ellipticals, and clusters of today, galaxies are monuments to gravity's power to sculpt harmony from disorder. Each galaxy, including our Milky Way, carries a legacy of collisions, chemical enrichment, and cosmic dance, a journey from anarchy to elegance. When you look up at the twinkling stars, you're not just seeing light. You're gazing at a universe that found order amid chaos, a cosmic symphony that invites us to explore its wonders for eons to come.